slot of an electrical machine. When you design an electrical machine, you should estimate the required power, the efficiency, and the power loss. And this power loss limits the electrical machine minimum dimensions. You cannot make the dimensions too small because the temperature will be too high, and the temperature is limited. For example, the temperature of the insulation class F should not exceed 155 degrees Celsius. In this example, we are going to simulate a slot of an electrical machine. In the slot, there is a stator winding, and the current flows in the conductors. There is the insulation around the conductors and the steel parts of the slot. Our task is to calculate the temperature distribution. Well, I'm going to simulate the heat transfer problem. And in heat transfer problem, you should specify the loss density, which is watts divided by the meter cubed. You can readily calculate this value from the current density and the resistivity of the material. And you see the heat is dissipated from the internal, external, and air duct surfaces. And in fact, the higher the air speed, the more heat could be dissipated. This is called the convection coefficient. And you see the convection coefficient is different for the external surface, for the internal surface, and then for the air gap. And the air temperature is different too. I am going to simulate only a single slot. On the left and on the right, there are similar slots. So instead of the simulating entire stator, I take only a single slot and set the symmetry boundary condition on the left and on the right. Okay. Let's start QuickField now. In QuickField, I create new problem. Slot. Next. Problem type is steady state heat transfer. Every simulated device is a three-dimensional object, but I'm going to simulate only a single cross-section, so the model class is two-dimensional plane parallel. Length units are millimeters. Finish. On the left you can see the problem pane, and on the right is the geometry model editor window. You can draw the geometry model here, or you can import the geometry model from the AutoCAD.exe file. I already have the drawing prepared in the card, so I'm going to import the model. Here you can recognize a stator. There are 36 slots. Temperature distribution in each slot is the same, so we can reduce the simulation domain. Switch to insert mode and draw the vertical line. Now edit, select all, edit, move selection, rotate by 10 degrees. Okay. And I will draw another vertical line. Now switch to select objects mode and remove the redundant parts. Select and hit delete button. Now this is the geometry model. I'm going to rotate it by 5 degrees. Move selection, -5. Now you may note that the model features vertical symmetry, and we can reduce the simulation domain even more. But the model looks simple, so I'm going to use it as is. Okay, let's assign labels. to labels, we can distinguish objects and provide material properties. Switch to Select Objects mode, click the object to select, and type in the label name here. This is steel. Click here, this is insulation. Click here, this is wedge. And these two blocks are conductors. Hold the Ctrl button pressed to select multiple objects at the same time. That's all for block labels, but I should also assign labels to the boundaries. These edges belong to the symmetry boundary. Symmetry. This is the outer surface of the stator, and these edges are inner surface. And these edges are cooling duct. So far, these are just text labels. Now let's provide physical properties for these labels. Double-click the label name in the tree. Thermal conductivity of steel is 25. Okay. Thermal conductivity of insulation is 0.15. Thermal conductivity of wedge is 0.25, and thermal conductivity of conductors is 380. And there is a Joule heat loss in the copper. I will type in the equation here. The Joule heat loss is resistivity, which is reciprocal to the conductivity, multiplied by the current density squared, amperes per meter squared, and this value I should type in again. Okay. Now for the symmetry, there is same slot on the right and the same slot on the left, so the thermal distribution on the left and on the right is the same. There is no heat flux running to the right or to the left. Heat flux is 0. The stator outer boundary is cooled by the air with a temperature of 20 degrees, and the convection coefficient is 10. The inner boundary is cooled by the air, but the air temperature there is 40 degrees, and the convection coefficient is 70. And in the air duct, the air temperature is 40 degrees, and the convection coefficient is 50. Okay. Geometry model and the data are ready. Before I start the analysis, I should build the finite element mesh. Just press this button and the mesh will be generated. Then save all problem files and solve the problem. Let's take a look at the results. Here you can see the color map of the temperature distribution, and I wonder which one of the conductors is hotter. I'm going to use the local values tool. Click any point and get the exact values of the temperature there. 83 degrees in the top conductor and 83 at the bottom. But there is a slight difference. The top conductor is a bit hotter than the bottom one. You can also use the contour tool. Here it is. I will draw the contour line and we'll get the temperature distribution along this line on the XY plot. This is steel part, then temperature drop in the insulation, bottom conductor, insulation, top conductor, insulation, and the wedge. And the exact values you can see in the table. Coordinates and temperature distribution. You can also use the contour to calculate integrals. I'm going to calculate the joule heat power integral. So contour clear, click here, integrals, heat flux. This is the joule heat power produced in both conductors per 1 meter of the conductor's length. Let's remember this value. Copy, paste it here. This is the total power loss. Now I wonder how much of the power is dissipated from the outer surface. Contour clear. Click here to select the outer surface. Heat flux. Paste. This is outer surface. Now let's measure the power on the inner surface. Contour clear. Click here, and here. This is the power on the inner surface. Also, the power is dissipated in the air duct. Contour clear. This is in the left duct. And I believe we will have the same value in the right duct. And the total should be 0. Let's find out. You see it is not 0, and the difference is caused by the calculation error. In our case, the error is 8%. To reduce the calculation error, you can use the solve and refine precision. Just click. OK. The mesh will be refined, and you should get more accurate results. Now let's check again. This is the joule heat value. Now let's find the heat flux from the outer surface. Contour clear. And from the inner surface. And from the air duct. From the left air duct. And from the right air duct. Now let's again sum up these values. You see the difference now is much less. 3%. You can repeat solve and refine precision again to get more accurate results. If you search for the slot of an electric machine on our website, you will find the example page. Here you can read about problem setup, browse the solution section, take a look at the resulting pictures, and download the simulation files. Simulation files may be opened and the results can be viewed using any QuickField edition, including QuickField Student Edition, that you can download from our website for free.